Hello and welcome everyone. Let me introduce today's speaker. Richard Riley is a professor of biostatistics at the University of Birmingham and an NIHR senior investigator. He leads a team of statisticians undertaking applied and methodology research for healthcare, especially in regard to prognosis, prediction models, and evidence synthesis. He is passionate to improve the quality of medical research and promote the importance of methodologists and high methodology standards. Richard is Deputy Chief Statistics Editor for the BMJ, the Chief Statistics Editor for BMJ Medicine, and a co-convener of Cochrane Prognosis Methods Group. He is the lead statistician on various applied and methodological healthcare-related grants from funders including MRC and NIHR. He has published over 200 research articles and is the lead editor of 2 textbooks that you might have heard of them. Prognosis Research in Healthcare, published in 2019, and Individual Participant Data Meta-Analysis, a Handbook for Healthcare Research, published in 2021. Ladies and gentlemen, I give you Professor Richard Riley.
Thank you so much. And that was a very kind introduction, and it's a real privilege to be speaking to you all today. I know you've already published a number of IPD meta-analyses and are working very actively in this field and want to do more. So I really hope that this talk is valuable to you. Some of it may be, familiar to you. Other things may be a bit more advanced, but hopefully you'll get something out of it and it will lead to some discussion at the end. Okay, so let's crack on. So I'm going to just introduce some of the rationale and key steps of an IPD meta-analysis to begin with. And then I'll focus a bit more on some notable examples. And in that context, I'll talk about some of the statistical methods that are used, but also finish with some notes of caution, because this is not a perfect field. So part 1, rationale and key steps. So as you know, meta-analysis is a statistical approach that usually follows a systematic review, aiming to synthesize quantitatively the results from multiple studies. It's from the Greek meta, which means after, above, or transcending. I like to think that as a meta-analysis, my work transcends everything that's gone before, but that would be very self-indulgent, wouldn't it? But basically, we're putting together evidence across multiple studies. And as you'll know, a traditional approach to doing a systematic review and meta-analysis means that we go to the study publications and we extract results from those publications. So for a meta-analysis of trials, we're obtaining estimates of effects, such as the treatment effect. So we'd be interested in measures such as odds ratios, risk ratios, mean differences, hazard ratios. And we'd also be interested in a measure of uncertainty about that estimate, a standard error, a confidence interval. So we're hoping that those things are available in those publications. So in theory, this is the quickest thing and the cheapest approach to take. If everything was well reported, we should be able to go to those publications, extract the information that we want, and do our meta-analysis. And then you'll know of familiar meta-analysis methods, perhaps like inverse variance methods, things that are embedded in tools such as RevMan, the Cochrane software. And this leads to nice forest plots, visual summaries that we see in publications of meta-analyses. So here's an example, a meta-analysis of 10 hypertension trials. So each of these trials is looking to see whether, compared to placebo, antihypertensive treatment reduces blood pressure. So negative values means a benefit. And we see that all of the studies, here are 10 studies in our meta-analysis, all of the studies have estimates that are negative, suggesting a greater reduction in blood pressure for those receiving antihypertensive treatment. And when we do the meta-analysis across studies using some weighted average, we have this overall pooled result suggesting about a 10 greater reduction in blood pressure for those that are treated compared to control. So this is a forest plot. This is a typical summary of an evidence base containing 10 studies, each with different numbers of participants. So the weighting of each of the studies is slightly different, but we get our meta-analysis pooled result, and that's the result that we're sort of interested in, because we think that that gives a summary for decision makers who are needing to decide whether this treatment is beneficial or not. So there are thousands and thousands of meta-analyses in the literature, but with this traditional approach of going to study publications, we are faced with a number of disadvantages. So briefly, we're reliant on how papers are reported. We know that there's often poor reporting. People still don't always give you effect estimates, may just focus on p-values. More importantly, as a statistician, I'm always a bit uncomfortable by the fact that someone else has done the analysis. So you've got the results in each study, but someone else has done the analysis of the data. So they may have used a different analysis method than you would have done. They may, for example, have not adjusted for prognostic factors or ignored complexities in the data. They may have given you a hazard ratio when you wanted an odds ratio, or vice versa. You're also quite vulnerable to publication bias, where studies that are not reported are more likely to be in a negative or non-significant direction. And also not all outcomes are going to be reported. So again, there's some sort of selective outcome reporting bias. And we also would struggle, wouldn't we, to go beyond what people did in the original paper. So they may have used the data to analyse the overall treatment effect, but if you wanted to look at patient level prognostic factor relationships, trends over time, interactions at the patient level, we would start to struggle because we don't have that information, because they didn't analyse the data that way. So we then have lost power to examine individual patient level responses. And in this era of precision medicine, we want to be doing those things. So it's a bit of a conundrum that we can't do those things very well with our aggregate data. So we can't look very easily at subgroup effects or prognostic factors and things. So you know where I'm building up to. This leads to many calls for individual participant data meta-analysis. We used to refer to this as individual patient data, but participant is a much broader, better, inclusive term. So let's use that from now on. What we're talking about here is the raw individual level anonymized data. And so an IPD meta-analysis is the synthesis in, again, usually a statistical model of the original data from multiple studies for the purpose of summarizing the evidence. And like I said, in this era of precision medicine, funders change how they want to market this. It used to be called stratified medicine 10 years ago, personalized medicine, there's various terms. Anyway, basically looking at how individual factors link to treatment effect or outcome risks and things like that. In the era of that, IPD, individual data, is surely very relevant. When we published our book a few years ago, we just looked crudely at the number of articles that cited individual participant or patient data meta-analysis. And you can see that in the last 10 years or so, there's been a huge increase in published articles. You could probably do this for any topic area and you get this trend. But anyway, it serves a point to say that there's more interest in this area than there was before. And I think in this era of data sharing, we should be thinking more and more about this, and people definitely are doing it. So just to clarify, here's an example IPD data set. And going back to those hypertension trials, if we think we've got the data at the individual level for those 10 trials, and we harmonize that data and we put it all together in a single database, then it would look something like this, where we would have to have an identification for the trial. We'd have to know the participant ID in each trial. We'd know whether they were treated or not for each patient. So we'd know each patient's age. We'd know their blood pressure before treatment. We'd know their blood pressure at 1 year. Now, think about without IPD, what you would have is the mean age in a study and the mean blood pressure at randomization. So you wouldn't know this individual information. Also note that crucially, I've still got an identification for trial here. I've not put this into one database and forgotten that there was clustering. and that's something I'll come back on to. In a different setting, I also work in cancer prognosis studies, and in that setting, you're more looking at sort of cohort studies, but the premise is similar. You'd have an identification for study, patient ID. You perhaps have more detailed information on some biomarkers. So here's various marker levels. For non-trial settings, you'd think about confounders or prognostic factors like age, stage of disease, and you'd have time to event information typically, so time to recurrence, time of death, length of follow-up and things like that. But we have this at the individual level. So because we've got individual level data, this allows many, many advantages. I'm not going to spend a lot of time on each bullet point, but just very quickly talk about some of these. We could be more consistent with our inclusion and exclusion criteria because we've got the raw data. We could reintroduce some people that were omitted before. For example, if some older individuals were admitted, we say no, we want to re-include them. We can account for missing data. Again, because you're in control of the analysis, you could account for missing data in the way that you want. You could use multiple imputation or another strategy that was appropriate. You can check the original study results if you wanted, so you can actually verify the original analysis results. We can inform risk of bias assessments. Come back onto that. We can obtain up-to-date information. So the trial may have carried on following up for 2 or 3 years after publication, and you may be able to get that data, so you'd have a longer follow-up period. We may be able to identify studies that have the same patients and deal with that. If studies were poorly reported, we can now include results based on the IPD, so we can calculate those results ourselves, not reliant anymore on the publication quality. One of the great benefits of an IPD collaboration is that when you ask authors for their IPD, and if of course they're willing, they might say to you, yeah, you can have our IPD for trial A, but did you know that we've also done trial B, but we never published it? And therefore they may give you more data, or they may say, actually, do you know about my colleague who's also done a trial? Have you asked them? So having this collaborative approach may lead to more data being available. We can standardize the analysis methods. So like I said, I like to be in control of what the analysis method was. Well, now I can be in control and I can standardize that. For example, I don't need to dichotomize continuous variables anymore. I can analyze them properly on their continuous scale. I can examine model assumptions. So are the hazards proportional? Is the hazard ratio a constant over time? We can account for prognostic factors. So I like to, in my analyses of trials, adjust for a few key prognostic factors. You know, you say, what is the treatment effect in a context where you know this prognostic information, their age, their stage of disease. And now I can do that in my analysis. I can condition on things. And this may allow us to reduce heterogeneity. One of the major problems of meta-analysis is heterogeneity across studies. And now we can maybe harmonize things, standardize things, and make the study results more homogeneous. We can examine individual level relationships at subgroups. Moving away from, I'll come back onto this big time later, moving away from trials, this is really valuable as well in other areas. So if you're looking at test accuracy studies, you can standardize what thresholds are used to define positive and negative. If you're looking at prediction models, for example, models to produce a risk estimate for individuals, we can develop models and validate them in multiple settings. And if you've got correlation, for example, you're looking at results at 6 months and 12 months and 2 years, they are likely to be correlated, and I can account for that correlation in my statistical modeling, which I wouldn't be able to do without the IPD. So I could keep going on and on about all the advantages, but I think you're probably on the same page as me that this is an exciting area to look at. And we are in an era of data sharing. Here's a paper that was published a number of years ago now in the BMJ, but basically confirming that the Institute of Medicine joins many other organisations, including the EMA and the NIH, in making clear that study reporting and data sharing in medical research are imperative, and the questions ahead are how, not whether. Many of us who publish research nowadays, the funder has a requirement that we make our data available. And therefore, in theory at least, IPD meta-analysis should be more feasible than they were before because of the requirements of our funders for data availability. But this isn't to say that we always need to do an IPD meta-analysis. So if you're in a situation where you're contemplating it, this is the sort of decision process that I would think about. So clearly, fundamentally, what is your research question? If you're thinking about population level average results, then it probably isn't necessary to get the IPD, because IPD is more relevant when you want to be thinking about individual level relationships. That's a crude generalization, but that's a broad thought. Has a previous review been done to answer this question? We may be thinking, okay, let's start with a traditional review based on publications and aggregate data, and let's see how far we can get with that. Maybe a previous reviewer said we can't answer this question without IPD. Also think about, if you were to do a traditional review, what aggregate data would you need, and would that aggregate data be available? Like I said, often it's not available. And also crucially, if you got the raw data, would it allow you to calculate the results that you want to? So there's no point obviously asking for IPD from trials where you're interested in a treatment effect at 12 months and they only followed up for 6 months. You know, you can't magic a trial to give you an outcome that they didn't record. So does it impact your decision to get the IPD from that trial? It does. How long will it take to obtain IPD? Anyone that's done an IPD meta-analysis project will know that this is extremely painfully long. It can take upwards of 2 years to get IPD, and you need to be prepared for that. You need to have funding in place. So have you got the resources to be able to obtain, collate, check and manage large sets of IPD that may come in dribs and drabs over a number of years? It's not something to be taken lightly. Do you have the experience in the clinical areas, in the statistical areas, in the data management areas to undertake this project? You know, again, I'm generalizing, but there's a broad set of people that would feel comfortable doing a standard meta-analysis of aggregate data. I think only a small proportion of those individuals would feel comfortable about doing an IPD meta-analysis. So all this is aided as well by collaborations. So I'm a statistician, but statistician is just one component of a big IPD meta-analysis project involving patients and clinical collaborators, data management experts, leaders in the field coming together to agree consensus and sharing of their data. So going back to that research question, like I said, I think the more nuanced your question is in terms of individual level relationships, the more the need for IPD, other things being equal. So if you're interested in the overall treatment effects, well, you know, a standard aggregate data meta-analysis, assuming the quality is fine and publication bias related issues are not particularly relevant, then the overall treatment effect should be answerable from a standard meta-analysis. But when you even looking at the overall treatment effects, if you want to say, well, I want to condition on a few prognostic factors, then again, you probably can't do that with IPD. But clearly, if you want to look at subgroups, you want to look at interactions between individuals and treatment effect. If you want to look at a nonlinear relationship for, let's say, how baseline blood pressure interacts with treatment effect, then, you know, that is not going to be answerable without the IPD. If you want to use the IPD for something new, because you want to develop a risk prediction model, so you're getting IPD from trials, but you want to use that data to examine prognostic factors or develop prediction models, then you can't do that without IPD. You can't. Also ask yourself the question, is the IPD going to improve the quality? So like I said, sometimes the IPD allows you to recover information that wasn't reported, like you could have more outcomes. You could standardize outcomes across studies. For example, you could convert from one scale to another. You may be able to improve risk of bias assessments. I'll come on to that. Think about the analysis methods within primary studies and whether you can improve upon them, and the reporting standards. So again, all these things are a thought process you need to think about. Do not just jump in to do an IPD meta-analysis. Really think carefully about whether it's achievable and whether the end product is going to be better than what you could have done without the IPD. If you've decided to do an IPD meta-analysis project, fantastic. Then think about these general scopes. Like I said, these are covered in the book that I wrote with Jane Tierney and Leslie Stewart. And it's such a big topic area. I'm not going to focus on each one in detail. I want to get to some of the statistical methods, but broadly, you develop the project scope, your research question and how you're going to undertake the project. Establish a central research team. One of the key things with an IPD meta-analysis project is you may have lots of noise from people who have provided you the data, and they may want to have influence on how you do your analysis, and they should be listened to, but you need to establish a central research team who have the responsibility for delivering that project and will make the final decisions. And those decisions could be tough because they may involve telling collaborators we're not using your data, because actually when we looked at your data, we didn't think it was good enough quality. And there may be some difficult conversations to be had, but you need to establish, maybe in data sharing agreements, that the IPD project leaders are the ones in control of how they do their projects. Otherwise, you'll get into lots of conflict later on in your projects. You may have experienced that yourself. But the central research team should involve people who've got experience in doing IPD meta-analysis projects, with statistical knowledge, experience in managing and coding data, and very good communication skills. And obviously clinical experts and patient groups. But communication skills is very important because you're going to be communicating with lots of different people and chasing people for information to get their data. You need to get in principle agreement to collaborate from study investigators. So before a grant application, you probably need to know and have confirmation in writing that people are going to agree to give you their IPD, and that may help you with power calculations, for example, to think about, if I could get this amount of IPD, this is the power that I would have to do my study. Thinking about all the different sources of IPD, developing data sharing agreements. This is the thing that takes months. You're going to ask your institution to sort out data sharing agreements with many other institutions from around the world potentially. Honestly, that takes such a long time, and it's just painful because it's sort of out of your control. You can push it, but you're not really involved in that that data sharing agreement, and it can be a tough process. If you don't have that data sharing agreement in place, you're running a big risk, because what's happened to us in some projects is that when people have seen the results of the IPD meta-analysis, they've withdrawn their IPD. I know that sounds ridiculous, but that's what's happened. So they'll see the results and go, oh no, this is too similar to what we're going to publish in follow-up work, so we're withdrawing our consent. Or they look at the results and go, we don't agree with this. We once developed a risk prediction model using data, and they said, oh, it's too similar to a risk prediction model that we've already advocated, so we're pulling our data. If you have those data sharing agreements in place with details on what you can and can't do and who can publish what, and then that will help with that. Okay. I mentioned this a few times, but examining risk of bias. Risk of bias is the quality assessment of a study, but with IPD, what we can do is not now just use information from the study publication about the quality, but we can use information from the IPD. So you'll have a continual process really, where you have information from publications and protocols, and you may do an initial risk of bias assessment. So you may look at some studies and go, do you know what, it's not worth having their IPD because it's such a bad study, and then you don't even go there. But there'll be some where you get the IPD and you're able to improve some quality aspects. Like I said, you may be able to re-include some participants or analyze it in a different way, which would overcome some concerns that you had before. But IPD again would allow you to uncover some problems. So you may be able to look at, for example, at the baseline imbalance in prognostic factors and go, there's something really wrong here because there's such imbalance. Or you may look at the randomization over time and say, well, there was 20% of people in the first 6 months were randomized to treatment A, but in the last few months, 80% were. So what's happened there? So you may uncover some things that you just didn't know. So the risk of bias is a continual process, starting before you've got the IPD and then carrying on after you've got the IPD. And that's something that's not very well understood at the minute, I think. I think people would still base their risk of bias assessment on the original study publications and not think about using their IPD. Moving on now on to meta-analysis. So again, this is so quick, but let's assume you've got your IPD, you've checked it, you've harmonized it, you've merged it, and now you want to do the meta-analysis. And like I said, that can take 2 years to get to that point. But this is the fun stuff for me. Okay, so you're thinking about doing a meta-analysis, you've got the data. Now, what do you do? Well, there's 2 approaches you can use, either a 2-stage approach or a 1-stage approach. And broadly speaking, these often give you very similar results, and I'll go on into more detail. But you may think about extended analyses, such as looking at a subset of trials that you consider to be low risk of bias. You're maybe not going to get IPD from all studies, so you might think about including aggregate data from studies that don't provide their IPD. When we report our results, we should always think about reporting it transparently using PRISMA IPD guidelines, and then think about the stakeholders in mind, incorporate patient and policymakers in your dissemination thought process. Okay, so let's focus on the meta-analysis part. So a 2-stage approach. So if we just focus on a meta-analysis of trials, IPD, and we want to summarize the overall treatment effects, then the 2-stage approach follows 2 stages, 2 steps. So the first stage, we're typically going to use a regression model in each study. So we're trying to estimate the overall treatment effect. So if you've got a continuous outcome, you'd fit a linear regression model. Binary outcome might be a logistic regression. Survival model, Cox regression model, we'd think about that for survival data. So we get an estimate of the treatment effect as measured by a mean difference, an odds ratio or a hazard ratio, and a measure of uncertainty about those. And then the second stage, we would pool these in a traditional meta-analysis model. So you may have heard of a fixed effect model or a common effect model or random effects model. So what are we doing here? Well, actually what we're doing is mirroring what we do without IPD, except for in the first stage, we're deriving the aggregate data ourselves, whereas a traditional meta-analysis would get the aggregate data from the publications. So in some ways, the meta-analysis component here is going to be very, very familiar to most researchers who have ever done a meta-analysis, for example, in RevMan. So step 1, we reduce the IPD to aggregate data, usually via a regression-based model. And then the second stage, and I should emphasize, that's in each study separately. So we're analysing the IPD in each study separately to get those treatment effect estimates in each study separately. And then in the second stage, we pool the results that we've derived across the studies using a meta-analysis method. I don't think there's anything specific in R or other software apart from Stata for doing this, but Stata has a package called IPD Metan written by David Fisher. This does both of these stages for you. So you call in a data set and it would apply step 1, the regression approach of your choice to all those trials, and then second stage would be pooled, and it will give you the forest plots and all the meta-analysis results. So like I said, linear regression, logistic regression, Cox regression, we're getting an estimate of our effective interest. Here I denote that by theta, and its variance, measure of uncertainty about that estimate. And then the second stage, we can think about a common effect meta-analysis where we assume that all the effects in every single study are an estimate of an underlying single true effect, a common effect theta. or a random effects meta-analysis would allow the true effect to be different in each study, but there's an assumption that those true effects are similar to each other in some sense, and we want to estimate the average across those studies and also measure the between study heterogeneity. So let's go back to the hypertension trials, and we're going to look at an IPD meta-analysis of those hypertension trials. So we've actually got very big trials here. We've got about 30,000 patients across those trials, and we're looking to see the overall benefit of treatment effect. We want to summarize the distribution of treatment effects. We want to quantify the amount of between trial heterogeneity, and ultimately we want to go beyond the overall effect and look at effect modifiers, but let's just not do that just yet. So here's a sample of the data, exactly like I showed you before, where we have individual patient information about post and pre blood pressure, treatment group, age, sex, etc. in every single patient, in every single trial. Obviously, that's just a snippet. There's thousands and thousands of rows. So in a two-stage meta-analysis here, because it's a continuous outcome of blood pressure, I'm going to fit a linear regression model in each trial, sometimes called an ANCOVA model, where I'm going to model the final blood pressure and adjust in the model for the baseline blood pressure. And that's going to give me an estimate in each trial of the treatment effect. So this is just a summary of the aggregate data that I've obtained using the IPD. So in every single trial, I've just given you 3 trials for brevity. I know the number of participants, the mean age, the mean blood pressure, baseline and treatment, and then I've got my treatment effect. But I've derived these myself from the IPD. And then in the second stage, I'm going to pull my treatment effect estimates, and I'm going to use a random effects meta-analysis. I think there's going to be heterogeneity, and I want to model that heterogeneity in the overall effect. So this is the meta-analysis. So very similar to what I showed you earlier on, basically, is I've got my 10 trials, I've got my 10 treatment effects, and my overall meta-analysis results of about -10 suggest a benefit of hypertensive treatment. So this is an IPD meta-analysis, but I've calculated all of these study results myself using the raw data, and I've adjusted for baseline. Most trials would not have done that. Now that for me is an important advantage here in this particular setting, because I've accounted for baseline blood pressure. But this may not have been needed. So remember what I said at the start, do we need IPD from all trials? Well, maybe not. Maybe actually most trials had used an analysis of covariance. They'd adjusted for baseline. Maybe they had reported the treatment effect estimate and given me the confidence interval. Maybe I'm not interested in going beyond the overall treatment effect. So in that situation, did I really need to do an IPD meta-analysis? Like I said before, most IPD meta-analysis would want to go beyond that previous graph and start to look at individual level relationships. Yes, I've adjusted for baseline. That's an advantage to me. But is it worth a 2-year wait? Is it worth 2 years of your time just to adjust for baseline? I'm not sure it is. But like I said, that's not the end of the story, because we want to go beyond, maybe look at more outcomes, more subgroups, deal with inconsistent methods. A bigger picture may emerge why those 2 years would be worth it. We could also have used a one-stage IPD meta-analysis. Now, I've looked at some of your papers and I can see that you tend to focus on IPD meta-analysis methods using a one-stage approach. Absolutely fine, but need to be careful because these models are quite difficult to specify correctly. So this is where we're analysing the IPD from all studies all together in one analysis. So whereas before we analysed each study separately and then pulled the results, now we're not doing anything separately in each study. We're analysing it all in one go to get the results out at the end. Crucially, this must account for clustering. So I've seen that your papers do account for clustering. So clustering is going to be accounted for example, by having a separate intercept per study or a separate baseline hazard for each study. You need to recognise, for example, in trials that those trials were randomised within clusters within the particular trial itself. So that needs to be modelled. Basically, what we're saying is that each trial should be allowed to have their own baseline risk. And if you amalgamate data and ignore that, it leads to potential bias and imprecision of results. and some potentially harmful decisions. So account for clustering, but also when you adjust for prognostic factors, that should account for clustering as well. So there should be a separate prognostic factor effect of baseline for every single one of those 10 trials. Otherwise, we're making a strong assumption that the effect of prognostic factors is the same in every trial, which is a very strong assumption and potentially leads to some contamination of the randomization across trials. If we stratify terms by trial and we stratify adjustment terms by trial, and we use the same estimation methods in a 1-stage and a 2-stage, then usually we should get very similar results between 1-stage and 2-stage methods. If you don't get similar results and the data are not sparse, then you're doing something different. So you're using a different estimation method, or you're making stronger assumptions in your 1-stage model. That's a really important point to make. I would usually always do both 1-stage and 2-stage to get an understanding of whether my 1-stage model is likely to be misspecified in some sense. But there's a key exception here, and this is when events are rare. So if most studies only have a small number of participants, or the events are rare, so close to 0, less than 10, 20 for most studies, then the 1-stage approach is the best approach to take, because it models the exact likelihood. So rather than pooling results in the 2nd stage where you assume they're normally distributed, you avoid that assumption, and you can just model, for example, in a logistic regression, you model the binomial data directly. But even in that situation, you can get some issues if you do not center your covariates. So when I say center your covariates, what I mean is that even, for example, the treatment variable should be centered by the proportion treated in that trial. Because by doing this, you disentangle within trial relationships and across trial relationships. And this disentangling can lead to better estimates of, for example, T-squared, the between study variance, and also separates out within trial and across trial relationships at the individual and study level, because otherwise you start amalgamating those things. So I'm going to come back onto these things in the last parts of my talk here. So first of all, I said 1-stage and 2-stage should be similar. So let's go back to those hypertension trials. And I'm going to use an approach called REML, Restricted Maximum Likelihood Estimation. And I do that in a 2-stage approach, and I get this result, again about -10 as before. If I did it in a 1-stage model, and I account for clustering, and I adjust for a separate prognostic effect of baseline in each of those 10 trials, and I've used REML, then I get basically the same result. Very similar estimates of T-squared and the overall effect. But if I'd used maximum likelihood estimation, so not restricted maximum likelihood estimation in a 2-stage, my T-squared would have been lower. So again, you can see the estimation method for your meta-analysis model is affecting your results. It's not the 1-stage or 2-stage per se, it's the estimation method for the model. If we said, okay, let's use maximum likelihood estimation, let's assume that's the right thing to do, then this is the 2-stage result. But the 1-stage result, if we didn't center, you can see that the T-squared estimate is much lower. If we did center our covariates by their means, then we get back to basically what the 2-stage is doing and the overall result. So it's really the model specifications that cause differences between 2-stage and 1-stage a lot of the time, and the estimation, rather than doing 1-stage or 2-stage per se. And that's something that people don't quite recognize, I think. Again, the big exception is when the data are small. So have a look at this example. This is a IPD meta-analysis of 7 trials, and we have sparse outcomes. So if you look at the control group, there are a number of trials with 0 events. In the treatment group, there's 1 trial with a 0 event. So sparse data, like I said, the 1-stage is more exact, and therefore actually the 2-stage approach will get you biased results in this situation. If we look at what happens, let's do a 2-stage. Now a 2-stage, I'm going to use maximum likelihood estimation just so I can compare it directly to the 1-stage. But for a 2-stage approach, if you were to work out the odds ratio in this trial, you couldn't do it because there's a 0 events. So you'd have to use a continuity correction, for example, adding 0.5 to each of the cells. So if we did that approach, we get a pooled odds ratio of 1.31, but a one-stage approach, which doesn't need any continuity corrections because it can model that data directly. And if we center our treatment variable to improve estimation of the maximum likelihood estimation, then we get a very different result than with 1.91. So, you know, these are not anywhere near each other. Now, the intervals are very wide. You wouldn't conclude anything particularly strong from either of these results, but it's just an illustration to say, yeah, actually, it is making a big impact in this situation of sparse data. Moving away from trials, test accuracy is another area where you tend to get sparse data. And what I mean by sparse here is that, for example, those that are diseased, most of them will test positive. So you have very few false positives. So it's sparse in that sense. So here's an IPD meta-analysis looking at the logit sensitivity of a particular test. You don't need to know what the focus is here, but there's 9 trials. You can see some trials, the number of true positives and the number of disease is 100%. So specificity is, you know, 100%. So we'd have to use a continuity correction there to do a 2-stage meta-analysis of sensitivity. But at 1 stage, we don't need to do that because we can account for the binomial data directly. And again, some big differences. So the 2-stage meta-analysis gets a logit sensitivity of 1.71. The 1-stage gets a logit sensitivity of 2.20. So here you're actually underestimating the sensitivity of the test by using the wrong meta-analysis method. Let's move on to moving away from overall treatment effects now and look at individualized prediction. Paul Gascoigne, many of you will know Paul Gascoigne, brilliant footballer for England. He once said, I will never make predictions and I never will. So obviously making a prediction, even though he said he wouldn't make one. This is what's happening in personalized precision medicine. We're trying to predict treatment effects at the individual level. So we want to tailor treatments to individuals. We want to look at prognostic factors. Let's just jump ahead to some examples. So this is the estrogen receptor in breast cancer IPD meta-analysis. This is what was found, that in those patients being given tamoxifen, those women with estrogen receptor positive are responding better to treatment than those that are negative. This was found by an IPD meta-analysis by, I think, the Oxford-led group, the Breast Cancer Collaboration. Amazing work. If we want to examine interactions, so the differences in subgroup effects, for example, then again, we can use a 2-stage or a 1-stage approach. We could use a 2-stage approach and estimate the difference in effects between subgroups, and that's called a within-study interaction, and average those in the meta-analysis. So instead of pooling the overall treatment effect, we pool the interaction. A 1-stage model, we can also get the interaction, but this is really quite a dangerous model to use because you need to very carefully disentangle factors that explain within study variability from factors that explain study level variability. And what tends to happen is that people just put in interaction terms, and that interaction term is then amalgamating within study and across study relationships. Again, you can deal with this in a 1-stage model by centering covariates by their mean. Let's look at the implications of what happens if we don't do this. Sorry, I'm just jumping ahead a little bit. This is back to the hypertension meta-analysis. This was the overall pooled result based on a traditional or a disseminator-led methods of movements estimator. So we have about -10, but this was the result across everyone. We might ask, okay, but is this equal for males and females? Then we're interested in what is the difference, i.e. the interaction between the treatment effect for males and the treatment effect for females. So here I've done a 2-stage IPD meta-analysis of the interaction terms. So each of these studies is now giving me the difference in the treatment effect between males and females. And on average across trials, the difference is very close to 0. And I would suggest that, not being a clinician, but that is a very small difference in blood pressure. So even if that was relevant statistically, it's not particularly relevant clinically. So there's no evidence of a difference in the treatment effect for males compared to females. And the difference is 0.77. But if we didn't have the IPD, what we might think about doing is looking to see the across-study relationship between the proportion of males in a study and the overall treatment effect. And if we did that, we would have this very strong relationship of 15. So without IPD, your best estimate of this interaction is totally different and hugely clinically relevant and statistically significant. But it's meaningless because this is an across-trial relationship. This is the result that you want at the individual level, and there's no evidence of a difference. Now, what people do when they do IPD meta-analysis is that they tend to amalgamate these results without knowing it. So the meta-analysis sticks an interaction term in a one-stage model, and you get an amalgamation, so somewhere between these two results. So be very cautious about one-stage models going forward unless you're carefully centering this information out. Right. Andrea Leadsom, when she was an MP, she said, "I have never and will not stop predicting the future. I don't do predictions ever." A few hours later on radio, she made a prediction. "I'm very strong arch Brexiteer. I genuinely believe that we have a bright future ahead of us when we leave the EU." You can't stop making predictions. People do it even when they say they don't do it. One area I think that I would encourage you to push towards if you're doing future IPD meta-analysis projects is non-linear predictions. So often we might assume that our interactions are linear between a continuous covariate like age. But here, again, this is the hypertension trials. What we're seeing is that there does seem to be, compared to this group here, which is a reference group of somebody aged 55, that in those less than age 55, the difference in the treatment effects, i.e. the interaction, it comes up, so it's less good because it's positive. Whereas in those over 855, there doesn't seem to be much difference in the treatment effects. So this is a non-linear relationship. What people tend to do is either assume age has a continuous effect, or that people categorize age into greater than 55 or less than that, which is nonsense. You will miss important relationships like this if you don't model non-linear interactions. The last few slides now. So risk prediction models I've mentioned a few times. This is another massive area where IPD meta-analysis could be beneficial. So this is a forest plot looking at the performance of a model in making predictions, and we measure this by calibration slope. And this is good when the calibration slope is 1. We had a model where we applied it in our IPD meta-analysis of 8 studies, and on average, it looks like it does well, but clearly it doesn't do well in this country or this country. But the meta-analysis average says it's fine. Well, this is a complete flaw of meta-analysis, isn't it? Because the average, it doesn't tell you about the effects in single countries. When you apply a model in practice, you can what's called recalibrate the model. So you can maybe change the intercept term to deal with different baseline risks. So with the IPD, we can look at this strategy. And here we can see that in this second situation where we apply it to the same data, but we recalibrate the intercept of the model, we now get, again, a overall estimate that's close to 1, but the heterogeneity that was there in the first situation has now pretty much disappeared. And if we were to predict the calibration slope in a new study or a new cohort of patients, it would be very close to 1, whereas before it was very, very wide. So recalibration of prediction models is another area to think about going forward for your studies. Added prognostic value. Doug Altman was one of the leaders of the meta-analysis world and one of the first people to do an IPD meta-analysis of prognostic factors. So this is looking to see whether a factor is associated with a future outcome. And when you look at published literature of prognostic factors, they're hugely subject to publication bias and poor quality. Doug's group with Marilena Travella, they obtained IPD to look at whether microvessel density was a prognostic factor in lung cancer. Previous meta-analyses without IPD had said it was very clear it's a prognostic factor. Doug's group got the IPD. They were able to analyze MVD on its continuous scale. They were able to adjust for age and stage of disease. And they looked to see whether it added value over and above age and stage of disease. And you can clearly see that actually after standardizing things and getting the raw data, there is no clear evidence of an effect. So it doesn't add prognostic value. This contradicted previous meta-analysis, and again, it's much more reliable. Going back to test accuracy, the key thing of test accuracy is to look at the effect of a test at multiple thresholds. Now, if you base this on publications, each study is going to use different thresholds, and that leads to an ROC curve which is not proper. You know, this should always be increasing, but without IPD, you get different numbers of results for each threshold, and therefore you lead to this weird ROC curve. But with IPD, you can analyze all the thresholds in every single study because you're in control, and you get this nice curve which is a proper monotonic curve. Right, last bit. I appreciate the time, and I'm going to spend 1 minute maximum on this. IPD meta-analyses are not always the gold standard. So, for example, you may not get all the studies you want. You may be very selective in how you get studies. You may only ask IPD from the studies you think are going to give you the answer you want. You may get selectivity in which studies agree to give you their IPD. So we do have to reduce our expectations of IPD meta-analysis projects, and that's what the England manager said when he was manager of England. He had to reduce our expectations of English football, and he certainly did that. It's also, like I said, costly, time-consuming. It's more complicated than the standard meta-analysis, but I'm just repeating some of the things I said. I'll leave you with this quote, which is quite dramatic. This is a letter to the BMJ. It says, why did it take 19 months to retrieve IPD from a non-profit organisation? The emails we received during the prolonged exchange were all friendly. Individuals involved were helpful, understood the need for data sharing, but they were hampered by inflexible, formalistic and slow bureaucratic procedures. Since our first inquiry, we communicated with 4 people, sent 25 emails, filled in 4 data use agreement forms and waited 1 year, 7 months. And that's just for one trial. So as well as being pro IPD, I'm also very cautious about people doing this without having good understanding of what's going to happen. So there's a summary of my talk, and there's a website, ipdma.co.uk, which I've tried to set up to help people new to the field, and I'll stop there. And I'm sorry for going about 5 minutes too long, but I hope it's been helpful.
Thank you, Richard. It was insightful. I think many people have got a lot of ideas and a lot of reading